Welcome back to Polymeric Biomaterials. We are now starting on a new theme. After looking at structure property relations, we are starting with temperature and solvent effects, which will be the theme for the next few lectures. And as part of this theme, as we have already mentioned in an earlier lecture, that effects of both temperature and solvent are unique for polymers. The focus of the next few lectures will be to look specifically at some of these effects. And we are interested in this both because temperature and solvents affect the processing of polymers or polymeric biomaterials for clinical applications, eventually impacting things like microstructure, which we will see today, as well as the fact that polymeric biomaterials are employed at 37 degrees in the body in the presence of an aqueous buffer. So, they are important both from the perspective of processing and from the perspective of eventual deployment in a clinical application. So, any testing, any structure property relationships that we come up with have to be contextualized against the backdrop of the fact that these materials will be used in an application that involves a specific temperature, namely 37 degrees Celsius, which is the body temperature, as well as the fact, whether we like it or not, the solvent that is present in the body is an aqueous buffer, which will have its own effects. So, with that background, we will start today's lecture, whose topic is polymer crystallinity and melting, where we are largely focusing on microstructure effects. So, we will look at polymer microstructure. We have mentioned crystal formation, crystallinity before and alluded to it briefly in previous lectures. In this lecture, we will look particularly at structural aspects of crystallinity and try to get a really good physical understanding of what crystallinity is and how it contributes to bulk properties later in the lecture. We will also see that you can think of crystallinity at multiple levels, where you can have hierarchy in microstructure, and we will have a chance to look at how that builds up over many length scales. We will also look at a model, for example, for semicrystalline polymers, which typically have both crystalline and amorphous domains. And while we will focus on amorphous phase and associated temperature transitions in a different lecture, we will have to allude a bit to the amorphous phase and the glass transition temperature in this lecture as well, for us to eventually understand crystallization kinetics. And as part of phase transitions, we will look at both melting and crystallization, and eventually end with how crystallinity can impact bulk properties. So, we will begin by first acknowledging that we are now dealing with the condensed or the bulk state. So, in previous lectures, for example, under the topic of conformations, we kept referring to the fact that in the melt state or in the presence of a solvent, many conformations are favored. But here we are looking at the condensed or the bulk state, the solid state if you will, where chains can now arrange in certain ways, giving rise to different types of microstructures, and those in turn can affect bulk properties. We are broadly interested in this lecture particularly in the effects of temperature, not just on chain organization and packing, but also on polymer microstructure. For example, we are interested in how different temperatures can lead to different transitions, phase transitions in polymers for example, and how crystallinity can be induced in polymers or not, depending on how fast or slow you cool the polymers from a viscous melt. So, you see temperature effects are present throughout some of these phenomena. Of course, again we will, as always, connect all of these to bulk properties, particularly mechanical properties. Now, one important philosophy again with this lecture is, our goal is to understand from a physical perspective, to get a really good physical handle on what crystallinity is. So, the crystalline state or the ordered state is largely characterized by the presence of a unit cell. And when we use the word crystalline itself or crystal, we are talking about long range order in the structure. So, that is the first thing that should come to your mind when you hear the word crystal or crystallinity. It is not just order, it is long range order. And the fact that they have an ordered structure means that they have very specific interactions with X-rays. In fact, one of the leading scientists whom we should sort of invoke at this point was a scientist called Hermann Mach, who is sometimes called the father of polymer science. He is a very, very important figure in polymer physics, and he lived right before the World War and lived through the World War. And in those days, he was one of the first people, along with Staudinger, to confirm the presence of things like unit cell and so on in polymeric microstructures. And he was also a very instrumental scientist in assessing or using X-ray diffraction as a means to understand microstructure. So much so that Linus Pauling, who himself was a Nobel laureate, was first introduced in great depth to these kinds of interactions by his interactions with Hermann Mach. Now, this word Mach, his second name, might also ring a bell. We have earlier in a previous lecture looked at the Mach-Hoving equation. It is the same Mach whom we are referring to here. He led a remarkable life. Imagine living in that period around the World War, living in Europe, and then escaping from Europe like many other scientists and moving across the sea to go to the US and pursue a career there, all for the love of science. So, there is a lot of inspiration we can draw from these great scientists. So, every now and then in this course, we will refer to some of these scientists, and my hope is you will go back and read more about them and draw inspiration from the wonderful lives that they led and the very difficult times through which they lived, and yet not giving up their passion for scientific discovery. So, the crystalline or the ordered state is also associated with what we would call first order phase transitions, the details of which we will look at later in the lecture today. And two examples of those are melting and crystallization. Tm and Tc simply represent the respective temperatures at which these events occur. Now, contrast that with the amorphous or the disordered state. Now, here the disordered state of the amorphous state is characterized by a lack of long range order. Now, it is important again to note that we are talking about long range, because if you really zoom in, you might see some localized maybe order, but there is no long range order at a higher length scale when you coarse grain a bit. And unlike the ordered crystalline state, the amorphous state is a non-equilibrium state, which means the amorphous domains under the right set of conditions can relax over time and also induce crystallinity with time. So, for some semi-crystalline polymers, for example, annealing them at certain temperatures can give enough thermal energy, just enough thermal energy for the chains to go past the glass transition temperature and over time start to relax. And it all comes from the fact that the state is a non-equilibrium state. And just as we have alluded to, this is associated with a second order like transition. One example of that is, one very famous example of that is glass transition temperature. Again, we will look at this in far more detail in another lecture, but for this lecture all we will say is that the glass transition temperature is simply a temperature below which the polymer behaves like a glass and above which the polymer behaves like a rubber. So, the temperature that marks the transition from a glassy sort of behavior to rubbery behavior is called the glass transition temperature. While we have talked about two different states, the crystalline or the ordered state and the amorphous and the disordered state, as two distinct classes, in reality what you will see is 100% crystalline microstructure in polymers is extremely rare. So, it makes sense to either talk about amorphous polymers or at best semi-crystalline polymers. So, you can talk about mostly amorphous materials or polymers or semi-crystalline polymers, and we have seen already examples of these. One example of an amorphous polymer that we have looked at, a copolymer, is PLGA, and an example of a semi-crystalline polymer that we have looked at is polycaprolactone. Interestingly, both are polyesters and both are degradable. Polymer crystallinity is not is an ongoing subject of research. There are some aspects that are very well understood, some aspects that are not very well understood. For linear chains, for example, fairly simple structures, the process is quite well understood, but for more complicated microstructures and architectures, the process of crystallization is not very well understood. So, it is a very interesting thing for us to look at a topic that is of great interest both in applied work and in fundamental research. And for now, we will simply add that 100% crystallinity is not possible because of largely kinetic limitations, and we will look at why later in the lecture, and also due to imperfections like branches or even chain ends that can't participate in the crystalline domains. So, having looked at a broad idea of what crystalline and amorphous states are, we will now start to look at a molecular picture of crystallinity by looking at it at 3 levels in terms of the microstructure. So, at the smallest level, we have already said that there is what is called a unit cell. One can think of a unit cell where the individual chains of polymers, which we have seen earlier in previous lectures, can pack to form these ordered structures called unit cells, not too different from the unit cells that you might be familiar with your understanding of other types of materials. And again, based on the work of Mark and others, it has been shown that these typically contain a few mers that are repeated in adjacent cells, maybe 2 to 3 mers depending on the polymer. And the distance between the cells or within the cell as a result is of the order of magnitude length scale of the bond length or the covalent bond distance itself. And you can have different types of unit cells formed depending on the type of polymer. For example, polyethylene will form is associated with an orthorhombic unit cell structure. Now, when you zoom out a bit and you come out, let us say you are focusing in with the camera, you are slowly coming out. Now, you will start to see that because of arrangements, regular ordered arrangements, these now unit cells can pack together into thin sheets or plate-like structures, which are called lamellae, which is just a name for the ordered structure that is found in polymers. Now, what is important to keep in mind here is that these lamellae that grow from these unit cells, so if you look at maybe a portion of this, you will find that within that region there are unit cells that are packed adjacent to each other. The lamellae thickness itself is not very long, it is about 10 to 20 nanometers, that is the order of magnitude length scale you are talking about, and it can grow to up to microns wide in the other 2 dimensions. So, these are thin plate-like structures and which are about roughly 10 nanometers thick. And what is interesting about this lamellar structure is one very characteristic feature of that is this idea of chain folding. These chains can fold this way 180 degrees and at the lamellar surface and re-enter the crystal and keep folding back and forth, leading to an ordered structure here. Now, if you zoom out even more, you will start to see that you can talk about another very important aspect of microstructure called as spherulite, which is simply the fact that it is a spherically shaped structure of crystallites. So, these lamellae that are folding etc., the chain folds, they splay, bend, branch etc., to form these 3D spherulites. Within the 3D spherulites, which is a radially growing, outward growing set of microstructures, you can have alternating crystalline and amorphous domains. So, the lamellae itself could come from here, whereas in between you can have tie molecules or disordered regions, thus giving you the alternating structure of amorphous and crystalline domains, and that is very interesting because that gives you a specific pattern or a signature when you use polarized light microscopy, as you will look at later in the lecture. And these are much larger, they can be 10 to 100 microns and are easily observable under an optical microscope. So, that is the 3 different length scales at which you can appreciate crystallinity from a molecular perspective. Now, if you consider a semi-crystalline polymer which has both crystalline and amorphous domains, one example of which we saw was polycaprolactone. One question we can ask now is, how do these long chains actually fold and form these very tight lamellar structures? That is the question we are asking here. And one way to think about that is there are many models. One model that we are going to look at here is the folded chain model, where adjacent re-entry is often seen. What is that? We will look at in a minute. So, if you notice this cartoon here, it shows these folded chain crystallites or lamellae and different plates of these lamellae connected together by disordered amorphous regions, which are called tie regions or tie molecules. So, these typically represent chain ends, for example, which can't participate very easily in the crystal structure itself. So, they remain dangling, and those can help connect multiple lamellae together as well. So, these 10 plate-like structures with chain folds at the faces, and as I said earlier, the chains that go out of the lamellar surface can fold back this way in what is called adjacent re-entry, where the chains re-enter the lamella by regular folding. But let us say this chain is no longer able to enter, there could be another chain that enters and that could take over and form the lamella. And likewise here, you can have another chain that takes over and builds up the lamella here. So, you can already see, although we are talking about a crystallite folded chain ordered region, even within the lamella you can have some defects that can reduce the overall crystallinity, and that is something that we should keep in mind. There are two aspects that are important when you look at something like this. One is a thermodynamic component, which simply sets limits on the maximum amount of crystallinity that can be achieved under a given set of conditions. That is what thermodynamics will tell you, but it will not tell you how long it will take, or in reality how much crystallinity can be achieved. That is the job of kinetics. So, while thermodynamics is very useful to set, thermodynamics is always interested in extremes and setting limits. This is the maximum that can be achieved, this is the maximum work that can be obtained from a system, this is the minimum energy, etc. Whereas kinetics will actually tell you in this case, in reality, what is the maximum amount of crystallinity that can be obtained. And as we have just seen, the lamellae are joined together by disordered regions which represent the tie molecules. And to get a sense of why these polymers, I call this a semi-crystalline polymer, why this can't actually achieve 100% crystallinity is because of a few different reasons. One is chain length and flexibility, chain entanglements, branching, chain ends and defects. So, if you have excessive flexibility, it is very difficult for some chains to come close together in a line and form these ordered structures. Likewise, if you have excessive chain entanglement, it is not easy for lamellae to form because these chains again have to come out and fold. So, excessive chain entanglement can also have detrimental effects on ability of a polymer to crystallize. Of course, things like branching and chain ends and defects will lower the crystallinity. Of course, the kinetic component again, which simply has to do with under that temperature, at that operating temperature in the melt, for example, what is the probability that these chains can come together and crystallize. So, all of that will be affected by these factors, and that in turn can help explain why many of the polymers or most polymers that we see can never be extremely crystalline, right. We can talk about 40%, 50%, 70% crystallinity, but achieving 100% crystalline polymers is only possible in the ideal case in theory. Now, having understood the folded chain model, we will now look at understanding crystallinity from a physical perspective, right. As we have already seen, in most of these polymers, crystalline and amorphous domains will coexist, and the actual degree of crystallinity will depend on a bunch of different factors. For example, temperature, the rate of cooling, the nature of the chain, molar mass and distribution. These are just some factors that influence the ability of a polymer to form crystals. Temperature, as we will see very shortly, there is a certain sweet spot temperature range over which crystallization can be favored. Below that temperature, chains do not have enough flexibility. Above that temperature in the melt, above another temperature in the melt, above the melting temperature, the chains are so dynamic and flexible that it is not easy for them to form these ordered structures at all. Rate of cooling, for example, can also have a very large impact on polymer crystallization. If you cool very fast from the melt, which is typically called quenching, then you do not give enough time for the chains to align themselves. So, you will lock in the amorphous phase, not giving a chance for the polymer chains to come together to crystallize. So, you see, one way to think about this is I am already talking about two time scales. One is a time scale associated with the polymer chains coming together, another is a time scale that is associated with the rate of cooling. Now, one way to think about whether crystallization is favored or not is to compare and contrast these two time scales. This is a very common approach in engineering, which is to understand some of these concepts by looking at time scales or length scales in the problem and comparing them to get a qualitative picture and a very good physical understanding of how things work. Later on, we will see something called a Deborah number. When we look at polymer relaxation, there also we are going to compare two time scales. So, you see, this will be a recurring theme, and what I would like you to ponder on is to compare and contrast. For example, the rate of cooling very fast, where you do not allow chains to sort of come together, thus you will not get the crystalline phase, but rather the amorphous disordered phase, as opposed to cooling at a controlled rate where you are allowing enough time for the chains to come together to form crystals. So, again, get a good sense of some of these mechanisms. It is very instructive to think of it in terms of the time scales associated with the problem. Of course, nature of the chain is going to have an effect, as we have seen. For example, if you have large side groups, they will affect the ability of these chains, for example, to come close to each other. Tacticity will have a role to play. If you recall from an earlier discussion, we saw that tacticity is one manifestation of configuration, and if you have atactic polymers where there is no order in the placement of the groups along the backbone, then it is not going to be easy for the chains with these disordered placements to come together and crystallize easily, as opposed to isotactic polymers where there is already some stereo regularity in the placement of the groups, thus promoting the ability of the polymer to crystallize more easily than an atactic polymer. And of course, molar mass will play a role as well. Longer chains will crystallize differently compared to shorter chains. The distribution also will have an effect because that also, the fact that different chains are of different lengths will also impact the amount of crystallinity achievable under a given set of conditions. Now, we are looking at here three different physical manifestations of crystallinity, and these are things that you can observe during phase transitions. And melt flow, for example, where when you heat a semicrystalline polymer, for example, and all the crystalline domains melt, you see changes to viscosity upon melting, and you get a viscous melt that starts to flow. So, that is one observation of or one manifestation of crystallinity that you can observe. Another is this idea of visual opalescence, where because of differences in densities between the crystalline and the amorphous states or amorphous domains, the crystalline domains tend to be more hazy as compared to amorphous domains which are more transparent. So, you will see a change going from the solid to the melt state. You can also observe this based on the interaction with X-rays. You will see very sharp X-ray diffraction patterns for the crystalline domains, which will give rise to simply broad halos upon melting. So, these are manifestations of crystallinity, physical manifestations that are observable under different sets of conditions. Note the importance of temperature in all of these things, and this is one reason why we are particularly looking at these effects in the context of temperature and solvent effects. That is the theme we are under. Now, at this juncture, it might be useful to stop and ask this particular question. For a contact lens biomedical application, would you really want a highly crystalline polymer? This is sort of a loaded question because if you really think about it, the way to approach this question is to ask what kind of properties are required for a contact lens application. If you are able to connect crystallinity to the optical properties as shown here, then you can immediately see that crystalline polymers will not be favorable both from the perspective of optical properties and from the fact that many of them will have very low oxygen permeability capabilities. That is why many of the polymers that have been used for intraocular lenses, polymethyl methacrylate, which are hard contact lenses that were used earlier, and another polymer which you can look up, polyhema, these are all polymers that are generally amorphous. And here is an example of microstructure directly impacting how these polymers are used in specific biomedical applications. So, that should give you a good appreciation for why we are interested in studying the microstructure, particularly crystallinity, in more detail in this lecture. So, having looked at the molecular picture, now let us now dig into a little bit of the mechanisms through which these phenomena occur, and our goal again is to understand both melting and crystallization from a mechanistic perspective, keeping in mind that we are interested in understanding the physics of these phenomena. These are what are called first order phase transitions, melting and crystallization, and here we are defining the melting temperature and crystallization temperature. Unlike small molecules, many of these properties for polymers will show a range. So, if you actually look at handbooks, for example, they might give you a number, but it will also have the tilde symbol, meaning it is approximate, or you might be given a range, and that is because crystallinity in polymers, the crystal sizes can be different, and when you heat it, the smaller crystals can melt first, the larger crystals will melt later, giving rise to a range of melting temperatures. It could be a small range, but the fact that it is a range, it's important. That's one of the distinguishing features compared to small molecules, for example. So here there are different ways to define these things. One working definition that would be useful for us, again from the understanding of the physics of these kinds of phenomena, is to define melting temperature as the temperature at which the last trace of crystallinity disappears with full scale molecular mobility in the polymer, right, going from a complete solid to a complete melt where there is no trace of crystal left at all. And crystallization temperature is that temperature below the melting temperature but above the glass transition temperature. Why that is so, we will see in a minute, at which crystallization is favored. So these would be good working definitions for us to look at for melting and crystallization temperatures. Now why are these called first order phase transitions? That is because events like crystallization and melting happen at constant temperature and pressure and involve latent heat, has latent heat involvement, and importantly they will show a discontinuity in the first derivative of the Gibbs free energy. So shown here are just two factors, two parameters. One is the pressure dependence of the Gibbs free energy at constant temperature, which will give you volume. The other is the temperature dependence of the Gibbs free energy at constant pressure, which will give you entropy. Both of these will show a discontinuity at any first order transition, melting as shown for example in this plot. So on the left side plot, you see that below the melting temperature of melting, the change in Gibbs free energy favors the crystalline solid state, and above the melting temperature, the change in Gibbs free energy favors the melt. And needless to add, at the melting temperature, these two phases exist in equilibrium, or in other words, the chemical potentials of the two phases are equal. Now you consider the first derivative of the Gibbs free energy, you can look at any of these, volume, entropy, etc. And when you have the ideal case where you have perfect crystals and so on, you will see a sharp transition and a sharp drop, that is a discontinuity at the melting temperature. Now contrast that with the real case, for example as shown here, which is linear polyethylene. You are cooling it from the melt. So you have the melt here and you are cooling it continuously, and what you see here is, while there is a change as the temperature decreases, there is a decrease in volume. Volume decreases rapidly but not sharply, and this you have to relate to the fact that these may not be perfect crystals. You may have crystals of different sizes that are forming based on the mechanism, etc., based on the defects. You can have a range, a short range over which this happens. One also important point to note here is because the melt is associated with a certain viscosity at a specific temperature, as you cool it down, you also have to keep in mind that the viscosity is going to go up significantly. So that will also affect the way in which these chains can align. So now you can perhaps understand why the cooling rate also matters. It's partly the thermal energy. From a practical perspective of processing it, you can also think of what happens to viscosity as you cool down these polymers from the melt. Now you can ask, what are the different modes or ways in which one can induce crystallinity? One is we have already seen, you can cool from the melt. You can cool to below the glass transition temperature at a controlled rate, and that is called dynamic crystallization. Now remember that if you cool too fast, which is called quenching, you will get only the amorphous phase, because you have not given enough time for the chains to align and form crystals. You can also do what is called isothermal crystallization, and then you at a controlled rate heat it up and go to a temperature where crystallization is favored and remain at that temperature in a process called annealing. So, if you anneal the sample at a temperature above the glass transition temperature where crystallization is favored at a fixed temperature, that is called isothermal crystallization. When earlier I said for semi-crystalline polymers, the amorphous domains over time can relax with storage. This is an example of what is happening here. At specific storage temperatures, if it so happens to be above the glass transition temperature of the polymer, even if you are storing it very carefully at a fixed temperature under controlled conditions, the amorphous regions can relax and you can start forming crystals. Again, depending on the kinetics of cooling, these chains may or may not crystallize to different extents. So, now we will, now that we have looked at melting and the first order phase transitions and how possibly one can induce crystallinity, now we can take a magnifying glass, go into the melt itself and start to ask what is the mechanism on the molecular level look like. So, we are now looking at crystallization kinetics using what is called a nucleation growth mechanism. So, now you are looking at a polymer in the melt which is greater than the melting temperature. These chains are like cooked spaghetti squiggling around. Now, this is an analogy we have seen earlier where we have said that you can think of polymer chains like an entangled mass of cooked spaghetti. Now, if you want to imagine them squiggling around, maybe a more realistic picture, if you are not grossed out by the analogy I am going to give you, is a mass of entangled long worms, if you will, that are sort of squirming against each other in a bowl and trying to come out. So, they are dynamic and flexible and they are constantly squirming around. I might have ruined spaghetti for you, but my hope is that gives you a much better picture of what is really happening in the melt for polymers. So, above the melting temperature, these chains are squiggling around, and remember, under these conditions, one thing that should come to your mind right away is the idea of conformations that we saw in an earlier lecture. Chain coiling or entanglement will depend upon the chemical structure, and again this is something we have seen earlier. Now, as you start reducing the temperature and cooling it in a controlled manner, you can start to have nuclei form either because there are impurities in the system itself or through localized segment aggregation, where chains, again because you are cooling it at a controlled rate, you give enough time for chains to start coming together as you are cooling it. Because remember, above melting temperature, the chains are so dynamic and flexible that even if they come together a little bit, the energy at that temperature is sufficient to again push them apart. But as you start cooling, you now provide enough time for those chains to come together, and once they start coming together, they can have some localized segment and aggregation and can start forming these folds and these lamellae like structures. And around the crystallization temperature, which again can be a range, these nuclei start to grow outwards through the inclusion of more chains and segments. So, you have these nuclei that form and they start to grow radially outwards by inclusion of more chains and segments. So, if you look at it more closely, what you will see is the same picture that we saw earlier. You can have multiple chains coming together to form these lamellae either through adjacent re-entry or wherein the same chain goes in and comes out, or you can have multiple chains coming in and going out. But in both cases, what you are forming is because of localized segment aggregation and around the crystallization temperature, you are forming these lamellae like structures. And as they start growing radially outward, you form at the larger length scales. If you zoom out a bit more, you start to see that the spherulites eventually form, which we saw on one of the earlier slides in this lecture. And eventually all of this stops because these spherulites keep growing, and eventually they will impinge against each other because they are growing radially, and you have to imagine this in 3 dimensions. They are growing radially, and they will eventually impinge against each other, and that is when crystallization will stop. So, you see, going from unit cell to localized chain folds to lamellae to spherulite to bulk, there is a clear hierarchy in the structure, and that is one of the characteristics of the crystalline phase. And just to show here as an example of a polarized light microscopic image of ultra high molecular weight polyethylene showing spherulites, which contain both amorphous tie regions and crystalline lamellae regions. And because of the way light can interact, polarized light for example can interact with these regions, get these phenomenon called birefringence, which you can read more and see what you are looking at is indeed an example of this effect. So, and you look at the scale bar here, you are looking at 200 microns. So, this is directly visualized under a microscope. Now, shown here is an example of polyethylene terephthalate, which is PET, which is a polymer that we have seen earlier, whose melting temperature is around 265 degrees and Celsius, and glass transition temperature is around 67 degrees Celsius. And if you are operating at a temperature that is above the melting temperature or at a temperature that is below the glass transition temperature, the crystallization rates are almost close to 0. Question is why? So, shown here is a plot of the linear growth rate of the crystals versus temperature. Now, remember that the melting point or the melting temperature of this polymer is 265. So, in this region here where you are above 220 or close to 260, 265, you have very high chain mobility, and the entropy of the system ensures that the disorder is retained, which means that even if chains occasionally can come close to each other, they are not going to be able to, they are so flexible and dynamic that they are not going to be able to form the ordered phase, because the disordered phase is favored under those conditions. Now, imagine the other extreme where you are looking at a glass transition temperature of 67. So, if you think of the region here where you are below or close to that, slightly only above that value, where you are, let us say, close to 80 or 70, the chains start to become sluggish, molecular motion starts to get arrested, because remember, Tg represents the glass transition temperature, which is a transition from the glassy to the rubbery state, where mobility is enhanced above that temperature, and molecular motion is mobility is arrested below that temperature. So, as you get closer and closer to the Tg, it becomes harder and harder for the chains to fold and be dynamic. They become what we call sluggish. And so, you notice that there is a sweet spot here where both nucleation and growth are promoted, and as you keep decreasing the temperature, this goes up, and then there is a temperature at which you see maximum rate of crystal growth, and then as you keep dropping the temperature, this again starts to go down. Another important idea related to crystallization is to ask, can we now use a mathematical equation to represent crystallization? And a very famous equation that you will find very often is called the Avrami equation, and this is used for isothermal crystallization, where the volume fraction of crystallinity at any time t is given by this equation, where there are two factors here, one is k and one is n. K simply happens to be the rate constant, which is a function of nucleation and growth rate. Larger the k value, faster the process is, and the exponent n simply tells you something about the mechanism of growth or nucleation and the dimensionality of the growth. We will not get into the details of examples or numbers for n and try to ask what is the mechanism there, but we will simply note that based on the exponent n, you get some information about the physics of the nucleation and growth and the dimensionality of the growth itself. And it should be quite clear that this equation can only be used for isothermal crystallization because you do not see the effect, the parameter for cooling rate showing up anywhere in this equation. So, right away this should tell you, there is a clue here that tells you that this cannot, this can be used only for isothermal crystallization. Now, this is one way to understand equations. If this not even a parameter that is showing up in the equation, then you can immediately tell that this cannot be used for dynamic crystallization. And there are other equations for dynamic crystallization. One example of that is the Ozawa equation, also called Ozawa-Avrami equation. It is again, the starting point is still the Avrami, but that will now incorporate, for example, the rate at which cooling happens, and then it will tell you what fraction of crystallinity you can expect. Now, having looked at the mechanism or the kinetics of crystallization, now we can ask, from a practical perspective, how can we quantify crystallinity? And we will look at a few different ways to quantify crystallinity. Firstly, noting that the following factors, again this is just a reiteration of concepts we have seen so far, factors that affect crystallization. As would be very clear to you by now, very close packing of chains that promote interchain interactions, namely secondary forces or interchain bonds that are promoted, that will lead to very quick and very easy crystallization. You want to have a temperature and a given set of conditions that allows sufficient quote unquote molecular flexibility, where if it is too high, then also you are not going to get crystallization such as above the melting temperature, or if it is too low such as below the glass transition, then also you are not going to get crystallization. We also note that controlled rate of cooling permits crystallization, while extensive chain entanglements will hinder crystallization. This is all looking at crystallization both from a temperature perspective and from a macromolecule chain perspective. Now, after noting this, we can now look at how to quantify this using different types of measurements. One very popular way to quantify percent crystallinity is to use the differences in density revealed by diffraction. Because there is a volume change that occurs, you can use that to quantify differences in crystallinity, and the degree of crystallinity on a volume basis is given as rho s minus rho a over rho c minus rho a times 100, where rho s is the crystallinity of the sample that is of interest to you, rho a is the crystallinity of the purely amorphous sample, rho c is the crystallinity of the purely crystalline sample, and rho a again is the crystallinity of the purely amorphous sample. So, from this you can get crystallinity using crystallinity based on volume. You can also have a similar equation on a mass basis, which I am not showing here, but I would encourage you to look at. It will look very similar to this, and you can try and look at that equation and see what the differences are and how you can perhaps go from one to the other if that is possible. Another quantification, another way to quantify crystallinity is this idea of crystallinity index, where the sharpness in the diffraction peaks corresponds to order in the crystal structure and the size of the crystalloids. So, crystallinity index here is defined as the area under the crystalline peaks under the Bragg diffraction line over area of the crystalline plus area of the amorphous halo. So, area under the crystalline peaks to total area of both crystalline and amorphous. So, this will give you something called a crystallinity index. You can also have, while these are based on diffraction experiments, you can also have another calorimetry based experiment that will also give you access to crystallinity, and that is this technique called differential scanning calorimetry. It is a very popular and extremely powerful technique to obtain a lot of information about thermal transitions in many polymers. Essentially, it relies upon having two different pans, if you will, and one pan you have sample, the other is the reference pan. Broadly what you are asking is how much heat should be supplied or removed from these pans to ensure that both pans are maintained at the same temperature. So, as you are heating it, if you want to keep both pans at the same temperature, and if the sample, the polymer, the sample in one pan undergoes a transition like melting or crystallization, that might involve removing or adding heat. And by tracking how much heat is added or removed such that both pans are maintained at almost the same temperature, you can get access to things like melting enthalpy. So, Poisson crystallinity here can be obtained by looking at the area under the curve for the melting enthalpy and dividing that over the melting enthalpy for a 100% pure crystalline polymer of the same sample, which can be obtained from the literature or handbooks. Now, shown here is a thermogram of polycaprolactone, where first of all you see that it says exo is up, and that is a nomenclature or a convention that we have used here. Exo can also be down depending upon the convention, but that has to be mentioned on the plot, otherwise it is not clear what kind of a thermogram you are looking at. And notice here that you are heating the sample, and as PCl is semi-crystalline, it can undergo melting at around 60 degrees. So, you see that there is a somewhat of a sharp peak at around 60, but it is also not extremely sharp as you would expect for very small molecules. And the area under this can be used to obtain information about delta Hm or the melting enthalpy. Sometimes what can happen is when you heat a sample like this, and if the heating rate is just right, and if the chain structure is so ordered that it promotes crystallization, you can get something called cold crystallization, where during heating, if it is done reasonably in a controlled manner, then you can locally above Tg, you can locally induce thermal, you can induce mobility within the chains, and that can lead to some localized reordering. So, in that case, sometimes you may end up getting something like this before the melting occurs. So, not only is the original sample with the original crystals are melting, the newly formed crystals during cold crystallization are also melting. So, in that case, you would not be using simply delta Hm over delta HMC, you would subtract the enthalpy associated with the cold crystallization to get access to the crystallinity in the sample itself. So, these are some caveats to keep in mind when one works with techniques such as these. It is a very powerful technique. In fact, some of these transitions that we are looking at, we will later see that towards the end of this course, that some of them can also be looked at for small molecule drugs, for example, where the amorphous phase for drugs is quite often important when they are prepared as amorphous solid dispersions, because the amorphous phase typically has higher solubility and higher bioavailability, but because it is non-equilibrium, it also will quickly relax to the crystalline state or revert to the crystalline state. So, large goal in pharma applications is to ask how do we stabilize the amorphous state of the drug, and that can be done using polymers that help improve the glass transition temperature of the system. Another rule of thumb, again this is what we would call a rule of thumb for looking at temperature of crystallization, if the melting temperature is known, is called the 8/9 rule, where the crystallization temperature is roughly 8/9 of the melting temperature. So, if you consider Tg and then you have Tm, somewhere in the middle you will have crystallization temperature. So, you see below Tg or around Tg, crystallization is not favored. Around Tm or above Tm, crystallization is not favored. Somewhere in the middle, crystallization can be favored depending on the polymer and the temperature. So, this is a rule of thumb, and for PET we are simply showing that this rule holds. Such rules of thumb are very common in engineering, and you will see them all the time. They work reasonably well, and they are typically used as a first pass approximation to estimate some of these values if another value is known. For example, if you know melting temperature, it is not very difficult to use this 8/9 rule with its own assumptions to access Tc. Now, with this understanding of crystallinity and crystallization, as we have already seen, things like chain branching, side group size, chain entanglements and tacticity, etc. can affect crystallinity. We now show that or see that crystalline polymers, or when I say crystalline I mean semi-crystalline polymers, those differences in crystallinity or higher degree of crystallinity has some significant impact on bulk properties. For example, highly crystalline polymers typically end up showing higher rigidity and density. If you remember, in an earlier lecture we talked about LDPE and HDPE, and the difference we saw was one of density, low density versus high density, literally low density and high density. You can now go back and ask, can I use my understanding of microstructure and crystallinity to perhaps help explain why one is low density and one is high density? And the answer will lie in how one of the polymer chains has a lot of long chain branches and the other one has minimal or very small branches, affecting how the chains can pack. Crystalline polymers, as we will see later when we look at solvent effects later in this theme, have higher solvent resistance. They have higher translucence that we have already seen because of the higher density. The way they interact with light will be different from the way they scatter better compared to the amorphous regions, and they have reduced gas permeability. So, now maybe you can revisit the question we asked earlier about whether you would want a highly crystalline polymer for a contact lens application, and these properties should clearly show you that that is not a very favorable microstructure at all for a contact lens application. You do not want a crystalline polymer for a contact lens application. And in that same vein, now would be a good time to pause and reflect or recall some of the things you have seen earlier and connect it to what we have seen now, which is we have seen tacticity, which you can now should be able to connect to crystallinity and to bulk behavior as well, and eventually we will be able to connect it to specific applications and their performance. We have just seen the example of contact lens. We will have a chance to see more examples of how highly crystalline microstructures can have specific types of mechanical properties, etc. later, but I would encourage you to revisit some concepts from lectures 7 and 10 and see how to connect them to some of the concepts we have seen here. They are all interrelated. And just to drive home this point with some examples, factors that favor induction of crystallinity would be polymers with regular structural arrangement, which would be linear polymers, for example. Stereoregular polymers that we have seen earlier in lecture 7 when we did configuration, we saw examples like polyethylene isotactic polypropylene. Because of already either the linear arrangement in polyethylene or the symmetric placement of the groups in isotactic polypropylene, it encourages or favors the chains to come together more easily. You can also occasionally have atactic polymers with very small polar or side groups where it does not have a large steric hindrance that can also help crystallization, or those can also crystallize easily. One example of that is polyvinyl alcohol. In contrast, factors that impede induction of crystallinity include stereoirregular or atactic polymers with bulky side groups, for example atactic polypropylene or polymethyl methacrylate. I would leave it to you as an exercise to go back and check the structures of these things and convince yourselves that this is indeed true. You can also have blends where blends of isotactic and atactic polymers of the same chemical structure will show reduced crystallinity, and that should also be obvious to you that the atactic chains will prevent here and there the isotactic chains from coming together, and it depends on the ratio of atactic to isotactic chains. And random copolymers also tend to be amorphous. Now, one important point to note here that crystallinity is not only critical for specific properties and performance, but we are also interested in these things because they are also of importance during processing of polymers. And one very important example of that is this phenomenon called spray drying in pharmaceutical applications, where we have so far looked only at cooling from the melt, but you can also induce crystallinity by evaporation of solvent, where because of saturation effects you can have polymers start to crystallize. And in spray drying, typically, which is used very popularly in pharmaceutical industries, if the goal is to prepare amorphous solid dispersions where the key is to prevent crystallization, where the key is to retain the drug, the excipients, the polymers, etc. in the amorphous state, you use this phenomenon, the process called spray drying, where the drying rates are so rapid that they will prevent crystallization. They will not give enough time for the chains to come together to crystallize. So, again you see the rate of drying and spray drying is now compared to the rate at which chains can come together, and because the time scale associated with drying are so small, that is, the drying happens so quickly that does not give enough time for the chains to crystallize at all, thus giving you what we call amorphous solid dispersions, which are a very important class of pharmaceutical formulations for drug release. And in conclusion, we will simply pause to list some examples of semicrystalline biomedical polymers that we have looked at so far. Linear polyethylene used, isotactic polypropylene used in hernia meshes, PTFE, which we have seen multiple times, polycaprolactone, polyglycolide and poly-L-lactide, and notice that we are using L-lactide here. DLLA, which consists of both D and L, we have seen earlier that is not the same as PLLA. So, these are some examples of biomedically or clinically important polymers that are semicrystalline. The other thing we will look at also is the effect on mechanical properties, and shown here is just one example of that. If you take two polyethylene samples and one is less crystalline, the other is highly crystalline, you can see that not only are there density differences, there are also significant differences in flexural modulus, or what we call flexural modulus, simply the quantification of the bending ability or the bending modulus of the polymer. And you see, for the same chemical structure, just depending on the degree of crystallinity, you can have very large differences in a property like flexural modulus, which is a mechanical property. And this plot here, or this diagram here, shows 4 quadrants where we are plotting molar mass and percent crystallinity, just to show the effect of the chain length and how that can affect crystallinity. So, you can have at very low molar masses and very low percent crystallinity, you will have soft and waxy kind of materials, and at low molar mass but very high crystallinity, you will have hard and brittle materials. At high percent crystallinity and high molar mass, you will end up getting strong and stiff materials, and high molar mass but low crystallinity, you will end up getting flexible kind of materials. So, you can now see the rich variety of mechanical or bulk behavior you can get simply by tuning the microstructure, going from low degree of crystallinity to a higher degree of crystallinity, and that is also in turn related to molar mass, as is clear from this. So, I hope that gives you a very good sense of how microstructure can be affected by temperature. That is one manifestation of temperature effects, the ability to form crystals, crystallization kinetics, as well as the fact that they can melt when heated. All of that is temperature dependent. But more importantly, what we have also been able to do is to connect the microstructure to bulk properties, which is a recurring theme throughout this course. More examples of which we will see in subsequent lectures.